Okay, so once again, we're going to go through and analyze the stability of the origin for a linear system. And so the first thing we want to do again is to look at our matrix A and determine its eigenvalues. So A is equal to 1, 3, 5, and 3. To find the eigenvalues, we once again subtract lambda off of the main diagonal. And we take this determinant and set it equal to 0. So it's 1 minus lambda times 3 minus lambda minus 15 is equal to 0. So that's 3 minus lambda minus 3 lambda plus lambda squared minus 15 is equal to 0. So that's lambda squared minus 4 lambda. And it looks like minus 12 is equal to 0. Factoring this, we're going to get lambda minus 6 times lambda plus 2 is equal to 0. So the lambda 1 value is positive 6, and the lambda 2 value is negative 2. Now we'll notice that since the one eigenvalue is real but positive, the other one is real and negative, we have eigenvalues that are of different signs. So this makes this a saddle node or saddle point. And the graph for this, if we were to put it all together, is going to once again contain two eigenvectors that we could find by calculating. And one of them is going to have directions going away. The other one will have directions approaching. And then our solutions, if we graph them, will be coming down towards the origin and away, towards the origin and away, towards the origin and away, and so on, and kind of like a hyperbolic saddle from calculus. But again, this is what we have when we have a saddle node. And again, these are definitely unstable since you start near the origin, but you don't approach the origin over time.